This video is a step-by-step solution for the example entitled Evaluating Isentropic Turbine Efficiency. In this example, you will learn about analyzing the expansion process for air across a turbine at steady state. We will also learn how to compute the isentropic turbine efficiency. Let's look at the problem statement as given to us. A turbine operating at steady state receives air at a pressure of P1 equals 3 bar and a temperature of T1 equals 390 Kelvin. Air exits the turbine at a pressure P2 equals 1 bar. The work developed is measured as 74 kilojoules per kilogram of air flowing through the turbine. The turbine operates adiabatically, and changes in kinetic and potential energy between inlet and exit can be neglected. Using the ideal gas model for air, determine the isentropic turbine efficiency. First, let's do a critical read of the problem statement, highlighting in red the important information given, and in green the information requested. Highlighted in red for the information provided, we have the following. A turbine operating at steady state receives air at a pressure P1 equals 3 bar and a temperature of T1 equals 390 Kelvin. The air exits the turbine at a pressure P2 equals 1 bar. The work developed by the turbine is measured as 74 kilojoules per kilogram of air flowing through the turbine. The turbine operates adiabatically, and changes in kinetic and potential energy between inlet and exit can be neglected. And also, using the ideal gas model for air. And finally, highlighted in green for the requested information we have, determine the isentropic turbine efficiency. Let's start to develop the solution. The first thing we have to do for any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in a critical read of the problem statement presented here in a bulleted list format. Air expands adiabatically through a turbine at steady state from a specified inlet state to a specified exit pressure. The work developed per kilogram of air flowing through the turbine is known. The next thing is to summarize what we have to find. This is again the same information we highlighted in green in a critical read of the problem statement, presented again as a bulleted list. Determine the turbine efficiency. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few important pieces of information that were provided, which will help us to develop our solution. The first thing to note is that there is mass entering and leaving the turbine. This immediately suggests that a control volume approach is appropriate. Having recognized this important fact, let's select a control volume boundary. In this case, it is selected to enclose the turbine and follow the physical boundary of the turbine as delineated on the schematic with the red dashed line. This control volume ties in the information provided, namely the inlet temperature and pressure at state 1, the exit pressure at state 2, and the work per unit mass of air flowing through the turbine. The next step is to develop the appropriate thermodynamic diagram to represent the process. In this case, the TS diagram. Let's highlight the diagram with the information provided. At state 1, the inlet pressure is P1 equal to 3 bar and the temperature is T1 equal to 390 Kelvin. Through the turbine, air is expanded to a pressure P2. Let's first consider the ideal adiabatic expansion from 1 to 2s. This is an isentropic expansion process with S2s is equal to S1. The process is represented by a vertical line on the TS diagram. For the actual expansion process from 1 to 2, the process is not isentropic and S2 is not equal to S1. The process is represented by a dashed line that is to the right of the isentropic process on the TS diagram. Note that the specific entropy increases due to the irreversibilities, and the exit temperature T2 is higher than the temperature at the ideal state 2s. The next step is to develop an engineering model, which is a set of simplifying assumptions which will allow us to perform the analysis of the problem. The control volume shown on the diagram is at steady state. The expansion is adiabatic, and changes in kinetic and potential energy between inlet and exit can be neglected. The air is modeled as an ideal gas. Having completed all the initial steps for our solution and represented the process on the TS diagram, let's develop the rest of the analysis. The actual work produced by the turbine is the numerator of the isentropic turbine efficiency equation shown below, and it has a known value. Eta sub T, or the isentropic efficiency of the turbine, is the actual work per unit mass divided by the ideal work per unit mass. The denominator is then evaluated as follows. The work developed by the turbine for an isentropic expansion from the specified inlet state to the specified exit pressure is given by the following expression. W dot over m dot sub s for ideal is equal to H1 minus H2s. From the ideal gas property table for air at 390 Kelvin, H1 is equal to 390.88 kilojoules per kilogram. To determine H2s, we use the definition of the relative pressure. PR at T2s is equal to P2 over P1 times PR at T1. Remember that the relative pressure concept is a convenient way to pre-tabulate the isentropic relationship between pressure and temperature. Keep in mind that a table of reduced pressure is built for a specific gas, in this case, air with K is equal to 1.4. Given the values of P1 equal to 3 bar and P2 equal to 1 bar, and PR1 is equal to 3.481 from the air table at T1 is equal to 390 Kelvin, we can substitute into the above equation and obtain the following. PR at temperature T2s is equal to 1 over 3 times 3.481, which gives us a value of 1.1603. By interpolating in a table, we get H2s is equal to 285.27 kilojoules per kilogram. After substituting H2s in the expression for the isentropic work presented earlier, we get the following. W dot over m dot for the isentropic case is equal to 105.6 kilojoules per kilogram. Recall the equation for the isentropic turbine efficiency shown earlier. And after evaluating the expression, we obtain the following. This gives us an isentropic turbine efficiency value of eta sub t is equal to 0.70 or 70%, which is the answer we were seeking. Quick quiz. Determine the rate of entropy production in kilojoules per kilogram of air flowing through the turbine. You may want to stop the video at this point to calculate the answer. The answer is 0.105 kilojoules per kilogram Kelvin. Hopefully, this agrees with the answer you obtained. If not, review this video carefully and check your calculations. If you still do not get the correct answer, here are a few hints. The rate of entropy production is given by sigma dot over m dot is equal to S2 minus S1. For air as an ideal gas, the entropy change can be expressed as S2 minus S1 is equal to S02 of T2 minus S01 of T1 minus R log of P2 over P1. From the solution shown earlier, the numerical values of S01 of T1 and H1 are already available. From the actual turbine work per unit mass given and the value of H1, H2 can be evaluated. In the table of air properties, you can then determine S02 at T2 is equal to 1.75613 kilojoules per kilogram Kelvin by interpolation corresponding to the value of H2. The numerical evaluation of sigma dot over m dot using the equation above is left as an exercise. In closing, in this example, we have learned about analyzing an expansion process for air across a turbine at steady state. We have also learned how to compute the isentropic turbine efficiency. This concludes the step-by-step solution of the example entitled Evaluating Isentropic Turbine Efficiency.